Hi, my name is Jiwon, and I am going to present SociaLite high-level query language for big data analysis. This started as a research project at Stanford, but now we are trying to make it a really usable open source project by collaborating with some of the big IT companies such as LinkedIn. So let me first talk about the motivation. So why do we need another big data analysis platform? Because we have plenty of big data analysis platform on Hadoop. Well, that's because those platforms have these problems. First of all, the existing platforms are too difficult to use, even for very experienced programmers. That is because the existing data analysis platforms provide too low-level primitives. Second, the existing data analysis platforms are somewhat inefficient because they are not designed to fully utilize the network bandwidth. And in most cases, the distributed data analysis programs should be network bandwidth bound, which is not the case with existing platforms. And on top of that, with existing platforms, if you want to do slightly different tasks, you need to learn very different framework. If you want to do large-scale graph analysis, you need to learn framework A. If you want to do big data mining, you need to learn framework B, which is very different from framework A. And if you want to apply simple relational operations, you need yet another framework. And that requires too much effort from the programmers. And that's why we came up with SociaLite. It's a high-level query language, and it's very easy and efficient. And the queries are compiled down to parallel and distributed code. And the compiled code is very efficient. For data analysis algorithms, it can be up to 1,000 times faster than equivalent Hadoop program if you run it on an InfiniBand network. If you run it on a 10 gigabit Ethernet, it's somewhere between 100 to 1,000 times faster than Hadoop. So we are Hadoop compatible, so you can easily read data from HDFS. And we have integrated SociaLite with Python, which makes it easy to implement some of data analysis algorithms. And this single query language is good for graph analysis, data mining, and relational queries. So with that, I'd like to give you outline of the talk. So first, I'm going to cover the programming concept in SociaLite. And then I'm going to show you some of the analysis algorithms implemented in SociaLite. And then I will show you some of the evaluation numbers, and then I will give you a demo. So distributed in-memory tables are the primary data structure in SociaLite to store user data. So these are column-oriented storage, meaning that the items in the same columns are consecutively stored in memory. You can use this kind of syntax here to declare a SociaLite table. You first write down the name of the table, followed by the column declarations. And the type of the column can be primitive types, such as int, long, float, double, or it can be object types, string, or any user-defined object types. Let me give you a specific example. So we have 4 table declarations here. And the first one here declares a table named foo having 2 int columns. An example of this table would be something like this, where we have 4 tuples. The second table declaration here has this parenthesis here, which means that you want the second column to be nested. So same set of tuples are represented like this with this table statement. So this comes in handy if you want to store, for example, graphs, edges in the graph. The third one with the angular bracket declares a distributed table where the table is horizontally partitioned and stored across the cluster machines. If you have two machines, then this bar table is partitioned into 2 pieces and stored across these machines. And the partitioning column with this angular bracket, which is the first column here, so the value of this column determines where the tuples should be stored. The last one has this 0.10 inside this angular bracket, which is called range operator. And this means that the value of this column is within that range, in which case we apply range-based partitioning, where if you have 2 machines, then tuples whose first column value is between 0 to 5 are stored in machine 1, and 6 to 10 are stored in machine 2. Compare this with the previous example where we applied hash-based partitioning. Okay. We also make it possible for users to control the structure of the table with these table options. You can add indexing to some columns, or you can declare applying sorting to certain columns, or you can declare that this is a multi-set rather than a simple set. So once you declare a table like that, you can use SociaLite rules to process the data and apply, for example, relational operations. Here is an example of SociaLite rule. What is on the left-hand side of this colon dash is called rule head, and what is on the right-hand side is rule body. So roughly what we're doing here is we are joining the tables in the rule body and inserting the join result into the table in the rule head. So let me give you an example. So let's say that we have these tuples before we evaluate this rule. So 5 tuples in bar and 5 in quotes, and foo is empty. So as we evaluate this rule, we go over the tuples in bar table, and for each tuple, we go over the tuples in quotes table to find the matching tuples, where the second column of the tuples in bar table matches with the first column of the quotes table. That is because we use the same variable name here, b, in the second column and first column. Okay. So for the first tuple here in the bar table, we have 2 matching tuples. So we do the join operation and store the result in the foo table. But only A and C, which is first column of bar and the second column of quotes. We have another matching tuple here. So after we evaluate this rule, we have 3 tuples in foo table. So let's have another look at this example where the tables are actually distributed tables. So if you have 2 machines, the tables are partitioned into 2 and stored like this. For the very first tuple in bar table here, we have a matching tuple in another machine. So we need to transfer this tuple from machine 1 to machine 2, which is automatically handled by the runtime system. So we transfer it to machine 2 and do the join operation, and transfer the join result to wherever it should be stored. In this case, back to machine 1 and stored in the right partition. So we accumulate some number of tuples in a temporary table and transfer the entire table in a single message. So we pipeline this communication and computation so that we can fully utilize system resources like CPU and network bandwidth. So if you use 10 gigabit Ethernet, we can fully utilize its entire bandwidth of 1 gigabyte per second. If you use InfiniBand, which gives you around 5 gigabytes per second, we can utilize a little less than 2 gigabytes per second, which is much better than any of the existing data analysis tools on top of Hadoop. Although all this communication is automatically handled by the runtime system, we make it possible for the users to control this communication pattern by the order of the tables in the rule body. So if you have the bar table first and then quotes table, then we try to transfer the tuples in bar table to where the matching tuples in quotes table are stored. But if you reverse it and have quotes table first and then bar table, then we try to transfer the tuples in quotes table to where the matching tuples in bar table. Okay. So going back to the previous example, if you have bar table first, then we know the value of B, which is in the partitioning column of quotes table. So we know exactly where the potentially matching tuples are stored. But in this case, where you have quotes table first, we do not know the value of A until we actually do the join operation. In this case, we need to broadcast the tuples in quotes table to the rest of the machines. Depending on the relative size of the tables and the partitioning schemes, this may or may not be better than the previous case. And we believe that this is something that programmers are typically roughly aware of. So we let the programmers to determine this communication pattern with the table ordering. But of course, in the future, it's possible for the SociaLite runtime system to optimize this to minimize the communication volume. Let me use the same rule here to describe how we make use of multiple cores. So the tables are partitioned, and each partition in each machine are further divided into sub-partitions, like the bar table here. And given a SociaLite rule like this, we create evaluation tasks, multiple evaluation tasks, as many as the number of sub-partitions in the first table in the rule body. So in this case, we have 8 sub-partitions. So we create 8 evaluation tasks like this. So each of these evaluation tasks operates on a single subpartition at a time. And these evaluation tasks are dynamically scheduled and executed by multiple cores in parallel. And synchronization code is automatically added if necessary, so users do not need to worry about the synchronization at all. So aggregation is very important in data analysis, so we support that in SociaLite. So the way how you apply aggregation is by having this aggregate function in the rule head. And the semantics is that for the tuples in the food table, we first apply the group by operation, where we are grouping the tuples by the values of the column who are before the aggregate function. So in this case, we are grouping by the first column value, A. And then we apply this min aggregate function to the tuples in the same group. And in this case, we only keep the minimum, whose second column value is minimum for each group. So we have built-in aggregate functions for common aggregate operations, such as minimum, maximum, summation, average, argmin. But we also make it possible for users to declare their own functions implemented in Java or Python. Okay, so one thing that makes SociaLite different from other kind of query language is that we support recursion. So recursive rules are indicated by having the same table in the rule head and rule body. And the semantics is very, very easy. So this rule is executed repeatedly until there is no changes to the table in the head. So we evaluate this rule once and add tuples to the full table. And with that added tuple, we evaluate this again. And that is repeated until no tuples are added to the full table. And this recursive rule with aggregate function, you can very efficiently implement some of core graph algorithms. For example, this shortest path algorithm here. So we have implemented single source shortest path algorithm, which is we compute the shortest distance from a single source node to the rest of the node in the graph. The graph is assumed to be stored in this edge table, source node, target node, and edge length. And the path table stores the result of this computation. So for each node, it stores the shortest distance from the given source node. And here we have a recursive query here having multiple rule bodies. And if you have multiple rule bodies, the semantic is simply you want to apply this aggregate function to all the tuples from all the rule bodies. The first guy here is the base case of the recursion, where you're simply setting that the shortest distance to the source node itself is 0. Okay. That is inserted into the head table and updates the path table, which triggers this recursive rule body, where we are going over the neighbor of the source node and update their distance from the source node. And if that is updated, then it may trigger another recursion, and this is repeated until there is no changes to the path table. And because of the characteristics of this, some of these aggregate functions, we can apply some of compilation optimizations, such as prioritized evaluation and incremental evaluation. The details of these conditions for aggregate function and the theory behind it is described in this paper, SociaLite paper in ICDE, and distributed SociaLite paper in VLDB. But basically what we can do here for this algorithm is we can compile this to Dijkstra's shortest path algorithm if you run it on a single core machine. And if you run it on a multi-core machine or a distributed cluster, we compile it to parallel delta stepping algorithm, which is one of the fastest parallel shortest path algorithm. So we have a Python integration, meaning that you can intermix Python code and SociaLite variables, SociaLite queries, as long as SociaLite queries are inside this backtick. So for this, we have extended Python interpreter to pre-process these queries inside the backtick. And we support full interoperation between Python and SociaLite. So from SociaLite queries, you can access Python functions and variables. And also from Python code, you can access SociaLite tables and the tuples inside the tables. So let me give you a specific example. So this shows how you intermingle Python code and SociaLite queries. We have a Python code here, and then we can mix it with a SociaLite query, where we define a distributed table and inserting a single inserting a single tuple into the table. And then we are defining a Python variable and accessing that Python variable from inside the SociaLite rule. The $ indicates that this variable is in Python. We also make it possible to use Python functions or Java functions inside SociaLite rules like this. But for the functions, we want you to annotate its return type so that we can optimize with respect to the return type. And on top of that, from Python code, you can iterate over the tuples inside this SociaLite table and print the tuples like this. So the Python code is sequentially executed, but the SociaLite rules are executed in parallel or in distributed cluster if you're connected to a cluster. And whenever you're running this script, when you're accessing SociaLite table like this, then we are fetching the tuples from the cluster machines to where you're running this script so that you can easily examine, for example, intermediate analysis result. So let me go over some of analysis algorithms, graph algorithms and data mining algorithms. So we have already covered shortest path algorithm. So now we have this Pagerank algorithm, well-known Pagerank algorithm. And in these 3-4 lines of code, we have implemented parallel Pagerank algorithm. So the first guy here is initialization, where for each node, we are setting the Pagerank value at iteration 0 is 1 over the size of the graph. So I don't have time to go over all the details. So let me compare this with Wikipedia description of the algorithm. So this is initialization, which maps to this orange guy. And at each iteration, you are running this equation, which maps to these guys. The constant part maps to the red rule body here, where the D is the parameter is called damping factor, and we're using 0.85 for this. And the second guy here maps to this rule body, where it actually uses link structure to compute the shortest, compute the PageRank value. What we are doing here is we are using PageRank value of node Pj at iteration t to compute the PageRank value of node Pi at iteration t plus 1. And Pi is the neighbor node of Pj, which is what we are doing here. So we are using the PageRank value of node Pj at iteration t to compute the PageRank value of Pi at iteration t plus 1, and Pi and Pj are neighbor node. And we are summing this up because we are adding everything here. So in my opinion, once you get to understand how SociaLite rules work, this almost looks like a pseudocode. And if you understand how this works, then you can easily come up with these SociaLite rules. Now let me go over some of data mining algorithms. K-means algorithms. K-means clustering algorithm is a clustering algorithm where given a set of data points, you are grouping the data points into K different groups. And the way how the algorithm works is initially you are assigning the data points to a random cluster. And at each iteration, you're kind of refining this cluster by first updating the center for each cluster by averaging the data point in the same cluster. And then with the updated cluster center, you are reassigning the data points to a cluster whose center is closest, which is basically what we are doing here. So we do not have the initialization, but here we are updating the center of the data point, updating the center of the cluster by averaging the data points in the cluster. And with that updated center, we are reassigning data points to a closer cluster using this argmin aggregate function. So in these a few lines of code, you have implemented parallel K-means algorithm. Similar for logistic regression, except that for logistic regression, we need a few more functions defined in Python because we want vector product operation or vector sum operation or the sigmoid function for the logistic regression. But basically, in these few lines of SociaLite rules and a few Python functions, you have implemented parallel logistic regression algorithm. So now let me give you some evaluation numbers. So we did 3 sets of evaluation to evaluate each single thread performance multi-thread performance, and distributed cluster performance. For the single-thread performance, we have implemented 6 graph algorithms, including shortest path, PageRank, and mutual neighbors, finding common neighbors for given set of node, and a few others. And we have implemented these algorithms in Java and Python. And the bottom line is SociaLite version is as fast as highly optimized Java version, which is around 30% slower than optimized C++ version. So this shows that SociaLite single-thread performance is reasonably good. Then we see how it scales over up to 16 cores. So for the same algorithms, we ran it on a multi-core machine from 1 to 16 cores. So the x-axis is the number of cores. And you need to look at the red line here. So the y-axis is scalability. So for these 5 algorithms, it scales almost linearly. With 16 cores, it's 16 times faster than when you run it on a single core. That's because these algorithms are massively parallel algorithm. And for shortest path algorithm, it scales a little bit sublinearly. So with 16 cores, it's around a little better than 10 times faster than when you run it on a single core. And this is because of the characteristics of the algorithm. And the optimal is, from the literature, is with 16 cores, it's about 12 to 13 times faster than when you run it on a single core. So that's the optimal, as best as you can do. But considering the flexibility of this query language, I think this is very reasonable. So I think this shows that the scalability on a multi-core is very good. So for the distributed performance evaluation, we have collaborated with Intel Research Parallel Research Lab to compare the performance of 4 distributed graph machine learning frameworks, including combinatorial BLA, which is distributed linear algebra library, GraphLab, a distributed machine learning framework, SociaLite, and Giraffe. And Intel people also implemented a native version for these algorithms with all possible optimizations. So this native implementation is very close to optimal. So we ran these 4 algorithms, BFS, PageRank, collaborative filtering, and triangle, on 1 to 64 machines. And of course, the native version is fastest with all the possible optimizations, including algorithm-specific optimizations. And for triangle benchmark, which is basically finding the triangles, a click of size 3, SociaLite is almost as fast as the native version, very close to optimal. And for the rest 3, SociaLite is slower than the combinatorial BLA. And for these 2 algorithms, BFS and PageRank, is noticeably slower. That's because for these 2 algorithms, combinatorial BLA has native implementation for these algorithms, whereas for collaborative filtering, we have actually used their API to implement this algorithm. So for collaborative filtering, the performance difference is smaller. And for all the algorithms, we are slightly faster than GraphLab and much faster than Giraffe. So I think this shows that the distributed performance of SociaLite is very competitive. And these are some of the things that we are currently working on. So we just started collaborating with one of LinkedIn team to apply SociaLite in an experimental project. So basically, we are trying to find some path between professionals in LinkedIn network. And we also started to integrate SociaLite with Yarn, the next generation research management framework. And also, we have just started to integrate SociaLite with these front-end frameworks, IPython and Gephi. So these are basically an interactive data visualization layer and more. And we want to integrate with this framework because to make it data analysis even easier. Okay. Well, this is summary, but I think I have time to go over this approximation in SociaLite. So we support some forms of approximation computation in SociaLite, and one of them is using Bloom filter to represent some of the columns in SociaLite tables. So let's go over this example here. So here we are computing friends of friends by joining friend table with itself and storing friends of friends in this FOAF table. And then we are going over this table to count the number of people having a certain attribute. Because of the small world characteristics of social networks, these friends of friends can be really large. So often, sometimes it's not possible to keep them in memory, in which case, in SociaLite, you can represent this second column of FOAF table in Bloom filter, using Bloom filter to save some memory. So if you use Bloom filter, you can use almost 1/10 of the memory compared to when you use a normal table, with some accuracy trade-off, around 92-3% accuracy. So basically what we are doing is if you represent the second column with Bloom filter, then we apply pipelined evaluation. So as we evaluate this rule and insert the tuple into the FOAF table, we pipeline that tuple and to this rule and compute this rule at the same time. That's because once you insert data into Bloom filter, it's not possible to enumerate the data, the items. So that's why we apply this pipeline evaluation. Okay, so now let me give you a demo. So I'm going to use DBLP data, which is not really big, but I think this is good enough for showing how it works. DBLP is basically computer science bibliography data. And we created a co-authorship graph out of DBLP data. So the vertices in the graph are the authors or people in DBLP. And the edges are co-authorship between the authors. So there is an edge between the two nodes if the two people wrote one or more papers together. Okay. Then we are going to examine some of Doug Cutting's academic network. So basically, we are going to simply run shortest path with Doug Cutting as the source node, and we're going to see how he is connected to some of well-known people. So let me, switch to, okay. So when you download SociaLite binary or source code, you can run SociaLite interactive shell like this. Cool. And have some Python code as well as SociaLite query. But for this demo, I'm going to use this Gephi interface. So you don't need to read the details, but on the left-hand side is the SociaLite interactive shell, and on the right-hand side is we are going to visualize the graph. So basically what I'm going to do is I'm going to copy and paste this script. Okay. And I'm going to describe what this does. So here, basically we are reading, the data co-author.txt file using this built-in read function, which returns the lines in the file. And then with this split function, we split each line with the tab, with this tab here. And then we cast it to integer and store it in the edge table. And here we are running the shortest path algorithm. We didn't copy everything, so yeah. So here I'm going to run this shortest path algorithm. Okay, let me run this rule once again. Somehow it didn't go through. Okay, and then I'm going to run this shortest path algorithm here, which runs almost instantaneously. And then the rest are just connecting SociaLite with the Gephi visualization layer. Okay, let me just copy this. And okay, so let me show you how Doug is connected to some of famous CS person. So I'm going to show path from Doug to Dan Knuth. So which looks like this, but I'm going to show the label and not just the label size. I'm not sure if you can read it, but basically Doug is connected to, so he wrote a paper together with David Karger, who wrote a paper with Professor Rajiv Motwani, who has a paper with Dan Knuth. So it shows how he is connected to Dan Knuth. And I'm going to show you a few more paths. I'm going to clear it and show path to Chris Olsen, the guy who created Pig Latin. So this is how Doug cutting is connected to Chris Olsen. So he's connected to Chris Olsen through Michael Lask and Jennifer Widom and Chris Olsen. Okay. So let me show you just one more example here. So another Pig Latin guy is Alan Gage. Do we have Alan Gage here? Alan here? Yeah, probably not. So he's another Pig Latin guy, and this shows how he is academically connected to Doug cutting. So through Michael Lesk again and this other guy. So Alan is about 4 number of hops away from Doug cutting. So we were able to do this selective visualization because SociaLite makes it very easy to query over the analysis result. So again, when you are connected to, I'm running this on my laptop, but when you're connected to a cluster, the analysis part runs on cluster, and you are fetching some of the data selectively and visualize it wherever you're running this GAPI interactive visualization tool. Okay. And do I have time? Yeah. And I think basically that's it. And if you have questions, this is a good time to ask questions. And also you can also you can come to SociaLite homepage, which is socialite.stanford.edu, where you can download the binary as well as source code in GitHub. So the source code is in Apache v2 license, so it's very liberal. So you can basically do whatever you want. So you can go to that homepage, socialite.stanford.edu, and play with SociaLite. Thank you. So if you have questions, this is a good time to ask. Yes.
So how does SociaLite compare with Apache Giraffe? I mean, are there use cases which are better handled in Giraffe than, say, SociaLite?
So in terms of performance, from our experience, right, so his question is how SociaLite compares to Giraffe, Apache Giraffe, right? Yeah. From my experience and from some of the people at Intel Research Lab, we felt that it's much easier to program in SociaLite than Giraffe. So Giraffe basically uses this vertex-centric programming model, which is very low level. So it's hard to break down the high-level analysis to vertex-centric programming model. So we found it much easier to program in SociaLite programming model. Okay.
And you said that the performance in SociaLite was better than in Giraffe?
So that's my experience and Intel Research Lab experience. So it was about almost 10 times or more faster. So there we used Apache Giraffe as of last year, December. Okay. Any other questions or? Yeah. and also, yeah.
What data sizes did you test this on in terms of size of graph?
For this, so we are currently keeping things in memory, right? So we are at the moment limited by the size of the memory, but we are storing data in real primitive type, not the box type, and we also support nesting, in which case you can save some memory for storing graphs, and we also support some forms of approximation, which could save some memory if you are willing to trade off accuracy. But basically, I think probably compared to other framework, I think we are probably, for the same data size, probably we have smaller memory footprint. So, any other questions? So I'll be here, so if you have questions later, if you want to ask me questions in person, just come to me after this talk. So, thank you.